For nearly a century, we have built a model of the universe that works extraordinarily well. It explains how the cosmos began in a hot, dense state nearly 14 billion years ago. It predicts the abundances of hydrogen, helium, and other light elements forged in the first minutes after the Big Bang. It accounts for the cosmic microwave background radiation, the afterglow of creation itself, with stunning precision. It describes how tiny quantum fluctuations during an early period of exponential expansion called inflation grew into the galaxies and clusters we observe today. The model is elegant, mathematically rigorous, and tested against countless observations. We call it the lambda cold dark matter model, often abbreviated as lambda CDM. Lambda represents dark energy, the mysterious force accelerating cosmic expansion. Cold dark matter refers to invisible particles that provide the gravitational scaffolding for structure formation. Together with ordinary matter and general relativity, these ingredients create our standard model of cosmology. This model is a triumph of human intellect. It synthesizes observations from telescopes studying visible light, radio waves, X-rays, and gravitational waves. It incorporates physics from quantum mechanics, nuclear physics, particle physics, and general relativity. It makes precise predictions that have been verified again and again. The cosmic microwave background has exactly the temperature predicted. Its tiny temperature variations match the statistical properties inflation demands. The large-scale structure of the universe, the way galaxies cluster along filaments surrounding vast voids, matches computer simulations based on lambda CDM with remarkable fidelity. Galaxy rotation curves, gravitational lensing, the dynamics of galaxy clusters all point to the existence of dark matter in the amounts the model requires. Supernova observations, the cosmic microwave background, and large-scale structure measurements independently confirm that dark energy constitutes about 68% of the universe's total energy density. The success is so complete that lambda CDM has become the default framework for understanding the cosmos. Every cosmology paper starts from this model. Every simulation implements its physics. Every observation is interpreted within its framework. The model has 6 fundamental parameters: the density of ordinary matter, the density of dark matter, the density of dark energy, the amplitude of primordial fluctuations, the spectral index describing how fluctuation strength varies with scale, and the optical depth to reionization describing when the first stars formed. Measure these 6 numbers precisely, and you can predict essentially every cosmological observable. This is remarkable compression of complexity into simplicity. 6 parameters describe 13.8 billion years of cosmic evolution across 93 billion light-years of observable space. Cosmologists have measured these parameters with increasing precision over decades. Early measurements had uncertainties of 20 or 30%. Modern measurements from the Planck satellite and other instruments have pushed uncertainties below 1% for most parameters. We know the age of the universe to within a few tens of millions of years. We know its geometry is flat to within a fraction of a percent. We know the expansion rate, the matter density, the dark energy density, all to exquisite precision. The model seems locked down, constrained by so much data that there is little room for alternatives, a definitive description of cosmic reality that will stand as one of humanity's greatest intellectual achievements. Except there is a problem. Actually, there are many problems. Not small technical issues that might be resolved with better measurements or refined theory. Deep, persistent discrepancies that have grown more pronounced as observations improved rather than diminishing as we hoped. The Hubble constant, measuring how fast the universe expands, gives different values depending on how you measure it. The disagreement has persisted for over a decade and widened as measurements became more precise. The early universe prediction does not match direct measurements. One or both must be wrong. Galaxies and galaxy clusters are distributed across the universe in patterns that seem more clustered than lambda CDM predicts. The distribution is lumpier, more organized, showing structure on scales that should not exist. The smallest galaxies behave differently than simulations predict. They orbit in unexpected patterns. They contain either too much or too little dark matter compared to theoretical expectations. The largest structures in the universe exceed size limits imposed by the age of the cosmos and the speed at which structure can grow. Each discrepancy can be explained individually with sufficient creativity. Perhaps we misunderstand systematic errors in one measurement or another. Perhaps our models of complex astrophysical processes, like star formation, are incomplete. Perhaps we are seeing statistical fluctuations, unlikely but possible outcomes from random variation. But as the discrepancies accumulate and persist, this becomes less convincing. The model that explains everything is showing cracks. Small cracks, perhaps, not yet wide enough to cause collapse, but present nonetheless. Visible to anyone who looks carefully, growing larger with each new precise measurement. This is not crisis yet. Lambda CDM still stands as the best description of the cosmos we have. No competing model explains observations as well across such diverse phenomena, but discomfort is growing in the cosmology community. Conferences now routinely include sessions on anomalies and tensions in the standard model. Papers question whether lambda CDM is complete, or whether it represents an approximation that works well in most regimes but breaks down in others. The possibility is being discussed openly that we might need to modify or extend the standard model. Add new physics, incorporate effects we have not considered, perhaps even reconsider fundamental assumptions. The situation feels familiar to those who know physics history. In the late 19th century, classical physics explained almost everything. Newton's mechanics described motion. Maxwell's equations described electromagnetism. Thermodynamics described heat and energy. A few small puzzles remained. The orbit of Mercury was slightly wrong. Blackbody radiation spectra did not quite match theory. The speed of light seemed oddly constant, regardless of observer motion. These were details, anomalies that would surely be resolved within the existing framework with better measurements or minor refinements. Except they were not. These small anomalies heralded revolutions. Relativity and quantum mechanics emerged from attempts to understand them. Classical physics was not wrong, but incomplete, a limiting case of deeper theories. Might we be in a similar situation now? Might lambda CDM be a classical limit of a more fundamental theory? Might the anomalies we observe be telling us something profound about cosmic physics that we have not yet grasped? The universe has been remarkably good at surprising us throughout history. Every time we think we understand it completely, new observations reveal unexpected complexity. We have no reason to believe this process has stopped. Lambda CDM is likely correct in many respects, but it may also be missing crucial pieces. Pieces that will only become apparent as we push observations to higher precision and explore regimes we have not yet accessed. The universe is trying to tell us something through these anomalies. We just have not figured out what yet, but the hints are there, the tensions are real, and they are forcing us to confront the possibility that our beautiful, successful, elegant model of everything might be incomplete in ways we are only beginning to suspect. The universe is expanding. Edwin Hubble discovered this in the 1920s by measuring the velocities of galaxies and finding that distant galaxies recede faster than nearby ones. The recession velocity is proportional to distance. This proportionality constant, the Hubble constant, tells us the expansion rate of the universe right now. It is one of the most fundamental numbers in cosmology. Know the Hubble constant, and you can calculate the age of the universe, the distances to remote galaxies, the rate at which space itself is stretching. This single number connects observations across cosmic history and provides a crucial test of cosmological models. If our model is correct, different methods of measuring the Hubble constant should give the same answer within observational uncertainties. They do not. Two approaches have emerged as most reliable. The first uses the cosmic microwave background. This radiation, from 380,000 years after the Big Bang, carries detailed information about the early universe encoded in its temperature fluctuations. Those fluctuations depend on the densities of matter, and dark energy, the curvature of space, and the expansion history. Measure the fluctuation pattern precisely, and you can infer all these parameters, including the Hubble constant. The Planck satellite did exactly this, mapping the cosmic microwave background with unprecedented precision. The result? The Hubble constant is 67.4 kilometers per second per megaparsec. This means that for every megaparsec of distance, about 3.3 million light-years, recession velocity increases by 67.4 kilometers per second. The second approach uses what astronomers call the cosmic distance ladder. Start with Cepheid variable stars, pulsating stars whose brightness varies periodically. The period relates directly to intrinsic luminosity. Measure the period and you know how bright the star truly is. Compare that to how bright it appears from Earth, and you calculate its distance. The Hubble Space Telescope has observed Cepheids in nearby galaxies, determining precise distances out to about 100 million light-years. Use those distances to calibrate Type Ia supernovae, stellar explosions that also have known intrinsic brightness. Supernovae are much brighter than Cepheids and can be seen across billions of light-years. Measure supernova distances and redshifts and calculate the expansion rate. Adam Rees and his team have refined this method to extraordinary precision. Their result? The Hubble constant is 73.0 kilometers per second per megaparsec. These numbers do not agree. The difference is small, only about 8%, but both measurements are now so precise, with uncertainties below 2%, that the discrepancy is statistically significant. More than 5 sigma, meaning the probability, this is random chance, is less than 1 in a million. Something is genuinely wrong. Either the cosmic microwave background measurement has undetected systematic errors, or the distance ladder measurement does, or both methods are correct, and something about our cosmological model is incomplete or incorrect. A decade of intense scrutiny has not resolved this tension. Dozens of research groups have checked both measurements using different instruments, different analysis methods, different subsets of data. The Hubble tension persists. If anything, it has grown worse as measurements improved. Early on, uncertainties were large enough that the measurements might have been consistent within errors. Now uncertainties are so small that the disagreement is undeniable. Both sides are confident their measurements are correct. Both have thoroughly investigated potential systematic errors. Neither can find a mistake that would reconcile the numbers. The implications are profound. If the early universe measurement from the cosmic microwave background is correct, then something is wrong with how we measure distances using Cepheids and supernovae. Perhaps Cepheid period luminosity relations are not as universal as we think. Perhaps Type Ia supernovae vary more than we believe. Perhaps metallicity, the abundance of elements heavier than hydrogen and helium, affects these relationships in ways we have not accounted for. Extensive studies of Cepheids and supernovae find no evidence for such problems. The physics seems solid, the calibrations appear correct. If the distance ladder measurement is correct, then something is wrong with the early universe. Perhaps dark energy was different in the past than it is now, evolving in ways the standard cosmological constant cannot accommodate. Perhaps the universe contains extra radiation beyond the known particles, affecting the cosmic microwave. Background interpretation. Perhaps the physics of the early universe involves processes we have not incorporated into our models. Each alternative requires new physics not present in lambda CDM. None has been confirmed by other observations. We would be modifying the model specifically to explain the Hubble tension, without independent justification. Or perhaps both measurements are approximately correct, and something fundamental is wrong with how we understand cosmic expansion. Maybe the expansion rate varies across the universe, not uniform in all directions as the cosmological principle demands. Maybe we live in an unusual region, a large underdense void where expansion is faster than the cosmic average. Maybe general relativity needs modification on cosmological scales. Maybe the relationship between redshift and distance is more complex than we think. Each possibility challenges basic assumptions underpinning modern cosmology. The community has explored all these options and more. Hundreds of papers propose solutions to the Hubble tension. Early dark energy models, where dark energy was stronger in the past. Interacting dark energy coupled to dark matter or ordinary matter. Modifications to gravity affecting how the universe expands. Systematic errors in observations that somehow evaded detection. New physics in the early universe, changing how we interpret the cosmic microwave background. None has gained consensus acceptance. None explains the tension without creating other problems or requiring fine-tuning that seems unnatural. Some researchers argue we should simply accept that one measurement or the other is wrong and wait for better data to reveal which. But this becomes less tenable as measurements improve and the tension persists. At some point, dismissing a 5 sigma discrepancy as measurement error is denial rather than skepticism. The data is telling us something important. Either our measurement techniques are flawed in ways we do not understand despite extensive investigation, or our cosmological model is incomplete. The model that explains everything struggles to explain this one number. The Hubble tension is not an isolated issue. It connects to other problems in cosmology, the tension over how clustered matter is, the unexpected properties of small and large structures, the anomalies in the cosmic microwave background, all might be related. Perhaps they are symptoms of a common underlying issue with lambda CDM. Perhaps the model is missing some crucial component that affects multiple observables in different ways. Or perhaps we are seeing unrelated problems that happen to emerge simultaneously as observational precision reaches new levels. Distinguishing these possibilities requires more data and deeper theoretical understanding. What seems clear is that we cannot ignore the Hubble tension. It is not going away. It is not being resolved through better measurements or refined analysis. After more than a decade of intensive effort by the world's best observational cosmologists, the tension remains. The expansion rate inferred from the early universe does not match the expansion rate measured in the nearby universe. Something is wrong. We do not know what, but the universe is telling us through this persistent disagreement that our model is incomplete, that we are missing something important about how the cosmos expands, or how we interpret observations, or both. The Hubble constant should be the most straightforward parameter in cosmology. Measure expansion rate. Get a number. Yet this simple measurement has become one of the deepest puzzles in modern physics, and it is forcing us to confront the possibility that the model we trust so completely might need fundamental revision. The universe is lumpier than it should be. Matter is not distributed uniformly across space, as lambda CDM predicts it should be on the largest scales. Instead, galaxies cluster together more strongly than expected. The distribution shows more contrast between dense regions and empty regions. Structure appears more organized, more prominent, more dramatic than our best computer simulations produce. This clustering discrepancy, measured by a parameter called S8 or sigma 8, represents another fundamental tension in cosmology. Like the Hubble tension, It has persisted and strengthened as measurements improved. And like the Hubble tension, it suggests something is wrong with our standard model. S8 measures the amplitude of matter fluctuations on scales of about 8 megaparsecs, roughly 25 million light-years. This scale is large enough to average over individual galaxies, but small enough to capture how matter clusters into groups and filaments. Lambda CDM makes specific predictions about S8 based on conditions in the early universe. The tiny temperature fluctuations in the cosmic microwave background seed all later structure. Their amplitude determines how strongly matter clumps as the universe expands. The Planck satellite measured these primordial fluctuations with exquisite precision. Feed those measurements into simulations of cosmic evolution, and out comes a prediction. S8 should be about 0.83, but direct measurements of clustering today give different values. Multiple techniques using different traces of large-scale structure all find that S8 is lower than predicted, around 0.76 to 0.78. The discrepancy is smaller than the Hubble tension, only about 3 to 4 sigma statistical significance, but it is robust, showing up in multiple independent measurements. Weak gravitational lensing, which measures how matter distorts the paths of background galaxies, gives low S8 values. Galaxy clustering itself, analyzing how galaxies are distributed in three-dimensional space, gives low values. Measurements of galaxy cluster abundances, counting how many clusters of different masses exist, give low values. The cosmic shear signal from the Kilo Degree Survey, the Dark Energy Survey, and other projects consistently finds less clustering than Lambda CDM predicts based on the early universe. The tension is opposite to the Hubble tension. The early universe prediction from the cosmic microwave background gives higher clustering than we observe today. This creates a puzzle. If matter clustered less than predicted, you might think gravity was weaker, or matter was distributed more smoothly initially. But the cosmic microwave background clearly shows the initial smoothness. The fluctuations have exactly the amplitude needed to grow into the structures we see, according to our models. Yet somehow the growth has not proceeded quite as expected. Matter has not clumped as strongly as it should have over 13.8 billion years of gravitational collapse. Why might this be? One possibility is that dark energy behaves differently than a cosmological constant. If dark energy was slightly weaker in the past, matter could have clumped more strongly, initially before dark energy slowed structure growth. But this does not match observations. We would see more clustering in the past and less now, opposite to what the tension implies. Alternatively, if dark energy was stronger in the past, it would have suppressed structure growth more than we think. This could produce the observed effect, but requires dark energy to evolve in ways we have no independent evidence for. Another possibility involves neutrinos. These ghostly particles barely interact with matter, but have tiny masses. Because they move at nearly the speed of light, they smooth out structure formation on small scales. If neutrinos are more massive than we think, they could suppress clustering enough to explain the tension. But neutrino mass is constrained by other observations, including particle physics experiments and observations of neutrino oscillations. The mass required to solve the clustering tension exceeds these constraints unless we are willing to invoke new physics like sterile neutrinos, hypothetical particles that interact even more weakly than standard neutrinos. No evidence for sterile neutrinos exists beyond the clustering tension itself. Modified gravity offers another approach. If gravity is slightly weaker on large scales than general relativity predicts, structure would grow more slowly than expected. Several modified gravity theories have been proposed specifically to address cosmological puzzles. Some work by adding new gravitational degrees of freedom. Others modify the relationship between matter and space-time curvature. These theories can potentially explain the clustering tension and the Hubble tension simultaneously, but they tend to be complex, requiring multiple new parameters, and often conflict with other observations like gravitational wave propagation speeds, which must match light speed precisely, as LIGO and Virgo observations confirmed. Systematic errors in measurements provide another potential explanation. Weak lensing measurements require precisely understanding galaxy shapes and how they are distorted by intervening matter. This is extraordinarily difficult. Galaxies have intrinsic shapes that must be averaged over to isolate the lensing signal. Imperfect understanding of intrinsic shape distributions could bias results. Similarly, galaxy clustering measurements require knowing precisely how galaxies trace the underlying dark matter distribution. If the relationship between galaxies and dark matter is more complex than we model, our clustering measurements could be systematically off. Extensive studies of these systematic effects have been conducted. They find some biases, but not enough to fully explain the tension. The clustering tension connects to other anomalies. If the universe is less clustered than predicted, this might relate to why we observe fewer small satellite galaxies than simulations predict. Less clustering means fewer small dark matter halos form, potentially explaining the missing satellites problem. But this connection is not straightforward because the scales are different. Satellite galaxy formation occurs on scales of kiloparsecs, while S8 measures clustering on megaparsec scales. Still, if some process suppresses structure formation generally, it might affect both. The tension also relates to the unexpected properties of the largest structures. If matter does not cluster as strongly as predicted, how do we explain the enormous walls and filaments that exceed theoretical size limits? You cannot have both less clustering than expected and larger structures than possible, unless the distribution of matter is somehow different than our models assume. Perhaps matter is more uniform on some scales, but more clumped on others. Perhaps the simple statistical description we use, derived from inflation and gravitational evolution, is not capturing some complexity in how structure actually forms. Recent years have seen growing attention to whether lambda CDM predictions are actually as robust as we think. The model makes specific predictions for the cosmic microwave background, and those predictions match observations beautifully. But translating early universe conditions forward 13.8 billion years to predict present-day clustering requires simulating enormously complex physics. Dark matter collapsing gravitationally, gas cooling and heating, stars forming, supernovae exploding, black holes accreting, galaxies merging. All these processes affect how matter clusters. Our simulations might not capture all relevant physics accurately. Perhaps the clustering tension is telling us our simulations are incomplete rather than that lambda CDM is wrong. But this explanation has limits. The simulations have improved dramatically over decades. Resolution has increased by factors of millions. Physics modules have become far more sophisticated, yet the clustering tension persists. If simulations were simply missing key physics, we would expect the tension to diminish as simulations improved. Instead, it has remained or even grown. This suggests the problem is not just simulation limitations, but something more fundamental. Multiple future observations will address the clustering tension. The Vera Rubin Observatory will measure weak lensing and galaxy clustering with unprecedented precision across half the sky. Euclid will provide complementary measurements from space. The Nancy Grace Roman Space Telescope will probe clustering across cosmic history. If the tension is real, these observations will confirm it at overwhelming statistical significance. If it is systematic errors or simulation limitations, improved measurements should resolve the discrepancies. Within the next 5 to 10 years, we will know whether the clustering crisis is genuine evidence of new physics or a false alarm. But for now, It stands as another indication that our model of the universe, successful as it is, struggles to match observations when tested precisely. Zoom into the simulated universe created by lambda CDM. Start with the cosmic web of galaxies and clusters spanning billions of light years. Zoom further into a region containing a large spiral galaxy similar to the Milky Way. Dark matter collapses first, forming an enormous halo extending hundreds of thousands of light years around the visible galactic disk. Ordinary matter falls into this dark matter halo, cooling and condensing into seas and gas that form the galaxy we observe. But the halo is not smooth and featureless. It contains substructure. Smaller dark matter clumps orbit within the larger halo, remnants of proto-galaxies that formed early in cosmic history. Some merged with the main galaxy, their stars now scattered throughout it. Others survived as distinct objects, orbiting the main galaxy like moons around a planet. These are satellite galaxies. Simulations predict hundreds of these satellites should orbit large galaxies like the Milky Way. The number depends on details of dark matter physics and galaxy formation, but even conservative estimates predict at least 100 satellites, massive enough to have formed stars and be potentially visible. Most would be small and faint dwarf galaxies containing thousands to millions of stars, rather than the hundreds of billions in the Milky Way. But they should be there. They're dark matter halos formed in the early universe. They should have survived to the present day as distinguishable objects orbiting in the outer reaches of the galactic halo. Except we do not see them. Astronomers count the satellite galaxies orbiting the Milky Way and find about 50. Not 500, not 200, 50. Even accounting for satellites too faint to detect or hidden behind the galactic disk, the observed number is at least 3 to 5 times lower than predicted, possibly 10 times lower depending on simulation details. This is the missing satellites problem, known since the late 1990s, and it has only become more pronounced as simulations improved and observations pushed deeper. The problem is not unique to the Milky Way. Andromeda, the nearest large galaxy, has similar deficits. So do more distant galaxies where deep observations have counted satellites. Everywhere we look, we find fewer small satellite galaxies than lambda CDM predicts should exist. This is systematic, not random. If simulations were roughly correct, some galaxies should have more satellites than average, and others fewer, balancing out statistically. Instead, essentially all galaxies observed carefully have fewer satellites than predicted. The simulations systematically overpredict. Many solutions have been proposed. Perhaps most small, dark matter halos never formed stars. Gas in tiny halos might have been heated by the first stars in the universe, preventing it from cooling and condensing, or supernovae explosions in small halos might have blown gas away before many stars could form. These satellites would still exist as dark matter clumps, but would be invisible. This sounds plausible until you calculate how much heating or gas removal is needed. The required energy exceeds what the first stars plausibly produced, and even with maximal feedback, simulations still produce more visible satellites than observed. Perhaps dark matter itself is different than assumed. Cold dark matter in simulations consists of particles that move slowly in the early universe, allowing structure to form on all scales, including very small halos. Warm dark matter, particles that move faster, would prevent small halos from forming while allowing large halos to grow normally. This naturally suppresses satellite galaxy numbers. But warm dark matter is constrained by other observations. If it is warm enough to solve the missing satellites problem, it produces other effects like delayed galaxy formation that conflict with observations of early galaxies. The parameter space that solves one problem without creating others is narrow or non-existent. Self-interacting dark matter provides another alternative. If dark matter particles can scatter off each other, not just interact gravitationally, This redistributes dark matter within halos. Simulations show this can reduce the number of satellite galaxies while better matching other observations like dark matter distributions in galactic centers. Some researchers find this promising. Others point out that the interaction strength needed is difficult to reconcile with observations of galaxy cluster collisions, which constrain how strongly dark matter can self-interact. Then there is the planes of satellites problem, making the mystery even stranger. The satellites we do observe around the Milky Way are not randomly distributed. About half orbit in a thin plane, called the vast polar structure, roughly perpendicular to the galactic disk. They move coherently, orbiting in the same direction. This should be incredibly rare, according to simulations. Dark matter halos form with random orientations. Satellite orbits should be scattered in all directions. Finding them organized into a coherent plane is like flipping a coin 100 times and getting all heads. Technically possible, but so unlikely it suggests something is wrong with assumptions. Andromeda shows the same pattern. Its satellites also preferentially orbit in a plane with coherent motion. So do satellites around several other nearby galaxies examined carefully. The pattern repeats. This cannot be chance. Something about how satellites form or survive creates planar structures. But nothing in Lambda CDM predicts this. Satellites should orbit randomly. Simulations virtually never produce planar structures as prominent as observed. Various explanations have been attempted. Perhaps satellites formed from tidal debris when smaller galaxies merged with the main galaxy. Debris can form streams that might look like planes, but this requires an implausibly large number of past mergers and makes predictions about satellite properties that do not match observations. Perhaps satellites formed preferentially along filaments of the cosmic web, feeding into the main galaxy. Filaments could create alignment, but observed satellite planes are not aligned with nearby cosmic web filaments. The missing satellites problem and planes of satellites problem together suggest our understanding of structure formation on small scales is fundamentally incomplete. We are not slightly wrong. We are wrong by factors of several to 10, and we are wrong in two different ways that seem contradictory. Too few satellites, but those we see are more organized than they should be. This combination is difficult to explain with simple modifications to Lambda CDM. Some researchers argue these problems indicate that our simulations are missing crucial physics related to star formation and gas dynamics in small halos. Perhaps the complexity of how the first stars formed, how their radiation and supernova affected surrounding gas, how cosmic reionization suppressed galaxy formation in small halos, all combine in ways our simulations cannot yet capture. As simulations improve, the problems might resolve. This is possible, but decades of improving simulations have not resolved the tensions. They have clarified them, and in some cases made them worse. Others suggest the problems point to dark matter being more complex than assumed. Not warm, not self-interacting in the usual sense, but perhaps interacting with hidden sector particles or having properties that only manifest on certain scales. This would be new physics beyond the standard model. It would require discovering what dark matter actually is, rather than treating it as a generic cold, non-interacting particle. After decades of failed dark matter detection experiments, we have no direct evidence for what dark matter is. Perhaps the satellite problems are clues that we have been looking for the wrong thing. The most radical interpretation is that Lambda CDM is simply wrong on small scales. That cold dark matter does not exist or behave so differently from assumptions that current models are inadequate. Modified gravity theories like MONDI make different predictions for satellite galaxy properties. Some claim better agreement with observations, though they fail to explain other phenomena that dark matter explains well. No alternative theory works as well overall as Lambda CDM, despite its problems with satellites. What is clear is that galaxies do not behave as simulations predict on scales of tens of thousands to millions of light years. The smallest galaxies are either missing or hiding in ways we do not understand. Those we observe are arranged in patterns that should not exist. This might be telling us something about dark matter. It might be telling us something about galaxy formation, physics, or it might be telling us something more fundamental about the model itself. Another crack in lambda CDM, another place where precise predictions fail to match careful observations. Another hint that the model explaining everything actually cannot explain quite everything. The universe is 13.8 billion years old. Structure grows through gravitational collapse. Dense regions attract more matter, becoming denser still. Less dense regions lose matter to their surroundings, becoming emptier. This process amplifies initial fluctuations, but it has limits. Gravity propagates at the speed of light. Matter can only fall together from finite distances in finite time. Calculate how far matter can collapse in 13.8 billion years, and you get a maximum structure size. Nothing larger should exist because there has not been enough time for gravity to organize matter across greater distances. Yet astronomers keep finding structures that exceed this limit, not marginally, substantially. These impossible structures challenge the entire framework of lambda CDM cosmology. The first hints emerged in the 1980s. Margaret Geller and John Huchra discovered the Great Wall, a vast sheet of galaxies stretching across hundreds of millions of light years. At the time, this pushed against theoretical expectations, but did not definitively break them. Perhaps initial conditions were slightly lumpier than average in that region. Perhaps our calculations of maximum size were too conservative. The structure was surprising, but not impossible. Then astronomers found larger structures. The Sloan Great Wall, discovered in 2003, spans 1.3 billion light-years. This exceeded naive estimates of maximum structure size. Theorists scrambled to show it could still form within lambda CDM, given rare but possible fluctuations. Computer simulations occasionally produced comparable structures if you let them run on large enough volumes. The probability was low, but non-zero. Finding one such structure in the observable universe was unlikely, but not impossible. Then came the Hercules Corona Borealis, Great Wall. Identified in 2013 through the distribution of gamma-ray bursts, this structure spans 10 billion light-years. 10 billion. The theoretical maximum is about 1.2 billion. This structure is nearly 10 times too large. It should not exist. The time required for gravity to assemble something this vast far exceeds the age of the universe. You cannot explain this with rare fluctuations or statistical luck. The probability of forming a structure this large through standard gravitational collapse is essentially zero. Yet there it is, undeniably present in the data. The issue is not just size, it is also probability. In a universe starting from nearly uniform initial conditions, as lambda CDM requires, large structures are rare. The statistics of how structure forms are well understood. Quantum fluctuations during inflation create Gaussian random fluctuations with specific properties. These grow through gravitational instability according to well-defined equations. The math predicts how common structures of different sizes should be. Finding one structure slightly larger than expected might be lucky. Finding multiple structures significantly exceeding size limits suggests the statistics are wrong. The universe is not distributed the way lambda CDM predicts. Several enormous structures have been catalogued. The giant void in Canes Venatici spans 1.3 billion light-years. The Shapley supercluster, the largest concentration of galaxies in the nearby universe, contains thousands of galaxies across several hundred million light-years and is more massive than predicted to exist at its redshift. The Boss Great Wall, found in 2016, extends across 1 billion light-years. Each discovery prompts recalculation of whether such structures can form within lambda CDM. Each time, the answer is maybe, barely, if conditions were just right and we got very lucky. The accumulation strains credibility. Beyond individual structures, statistical analyses of large-scale matter distribution find anomalies. The universe appears lumpier on very large scales than it should. Regions several hundred million light-years across show more density contrast than lambda CDM predicts. Not drastically more, not enough to completely invalidate the model, but consistently more. This is related to the clustering tension discussed earlier, but manifests on even larger scales. Matter is organized into structures that are both larger and more prominent than gravitational collapse from smooth initial conditions should produce. Why might this be happening? One possibility is that initial conditions were not as smooth as standard inflation predicts. Perhaps quantum fluctuations during inflation had a different statistical distribution. Perhaps inflation lasted different amounts of time in different regions, creating more variation. Perhaps cosmic strings or other topological defects left over from phase transitions in the early universe seeded additional structure. Each modification allows larger structures, but requires moving beyond the simplest inflation models that work so well explaining the cosmic microwave background. Another possibility is that dark energy was different in the past. If dark energy was weaker early on, structure could have grown faster before dark energy began dominating and slowing growth. This extended period of rapid structure formation might allow larger structures, but this requires dark energy to evolve in specific ways that we have no independent evidence for. We would be modifying lambda CDM specifically to explain the large structures without other observations demanding such modification. Modified gravity provides yet another approach. If gravity is stronger on very large scales than general relativity predicts, structure could grow faster and larger. Several modified gravity theories make such predictions, but they must carefully tune the modification to affect only very large scales without disrupting the successful predictions lambda CDM makes on smaller scales or altering light propagation in ways that conflict with gravitational wave observations. Threading this needle is difficult. Most attempts fail some observational test. Perhaps the issue is not physics but measurement. Defining what constitutes a single structure is somewhat arbitrary. The Hercules Corona Borealis Great Wall is not a solid object, but a region where gamma-ray bursts are more concentrated than average. Different statistical techniques give different boundaries and sizes. Maybe what we call one enormous structure is actually several smaller structures aligned by chance along our line of sight. This criticism has merit for some structures, but not all. Some of the largest structures show clear coherence across multiple wavelengths and traces. They are genuine concentrations of matter, not statistical artifacts. The fundamental tension remains. Lambda CDM predicts structure formation should proceed hierarchically. Small structures form first. They merge and grow into larger structures over time. The process has limits imposed by the age of the universe and the finite speed at which gravity can act. Structures beyond a certain size should not exist because there has not been time to assemble them. Yet we observe structures exceeding that size. Either our calculations are wrong, our understanding of structure formation is incomplete, or lambda CDM is missing crucial physics about how the universe evolved. This problem connects to others. The Hubble tension might be relevant because the maximum structure size depends on the expansion rate. If expansion was slower in the past than the cosmic microwave background suggests, more time was available for structure growth. This could allow larger structures. Similarly, if clustering was stronger than predicted, it would produce more prominent structures on large scales. The various tensions might not be independent problems, but symptoms of a common underlying issue. What is clear is that the universe has produced structures that challenge our understanding. We can calculate theoretically how large structures should be. We can observe how large they actually are. The observations exceed the predictions. Not by enormous factors, not so much that lambda CDM is obviously wrong, but enough that we cannot simply dismiss the discrepancy. Enough that we must consider whether the model is incomplete. The largest structures in the universe might be telling us something fundamental about cosmology that we have not yet grasped. That structure forms differently than we think, that the early universe had more variation than we realize, that dark energy or gravity behaves in ways we have not incorporated, or that lambda CDM, for all its successes, is missing pieces that only become apparent when we examine the universe at its grandest scales. The universe should look random. On large scales, after averaging over local irregularities, matter should be distributed uniformly in all directions with no preferred orientations. Galaxies should point every which way. Their rotation axes should be scattered randomly across the sky. The cosmic microwave background should show the same statistical properties in every direction. This is the cosmological principle, the foundation stating that the universe is isotropic and homogeneous. No special directions, no large-scale organization beyond the random patterns that emerge from initial quantum fluctuations. Lambda CDM builds on this principle. Every prediction assumes isotropy and homogeneity hold on sufficiently large scales. But observations keep finding patterns that should not exist. Galaxies align with each other across distances far too large for any physical process to coordinate their spins. The cosmic microwave background shows anomalous features pointing in specific directions. The distribution of matter appears asymmetric when analyzed carefully. Each anomaly individually might be statistical fluctuation. Together they paint a picture of a universe that is not quite as isotropic as it should be. Not dramatically anisotropic, not obviously violating the cosmological principle, but subtly, persistently, showing preferences for certain directions and alignments that should not occur if lambda CDM is correct. Start with galaxy spins. In 2014, researchers analyzing the Sloan Digital Sky Survey found that spiral galaxy rotation axes were not randomly oriented. Across regions spanning hundreds of millions of light years, galaxies showed a tendency to align with each other. Their spin axes pointed preferentially in similar directions. The alignment was weak. Not every galaxy participated, but statistically significant. Far more galaxies aligned than random chance would allow. This should be impossible. Galaxies separated by such vast distances have never been in causal contact during the era of galaxy formation. No physical mechanism can coordinate their spins. Yet the correlation exists. Follow-up studies gave mixed results. Some confirmed the alignment using different galaxy samples and different analysis methods. Others found no significant signal. The scientific literature became confusing, with contradictory claims about whether alignments were real. Part of the problem is defining galaxy orientation from two-dimensional images. Spiral galaxies seen edge-on look different from those seen face-on. Disentangling viewing angle from true three-dimensional orientation is difficult and subject to systematic errors. Different research teams made different choices about how to handle these issues and reached different conclusions. But some studies found alignments too strong to easily dismiss. One analysis suggested galaxies in one hemisphere of the sky preferentially pointed toward the northern galactic pole, while galaxies in the opposite hemisphere pointed away. This created a dipole pattern, a large-scale asymmetry in galaxy orientations. If real, this would directly violate isotropy. The universe would have a preferred axis. No process in lambda CDM can create such a dipole. Initial conditions from inflation should be isotropic. Gravitational collapse from isotropic initial conditions cannot spontaneously create preferred directions on cosmic scales. Galaxy alignments connect to the cosmic web structure. Galaxies form within dark matter halos that are part of larger filamentary networks. Gas falls into galaxies along these filaments, potentially creating torques that spin galaxies in directions related to filament orientation. Computer simulations show this can produce alignments on moderate scales, tens of millions of light years, but observed alignments extend over hundreds of millions of light years, far beyond what filament-induced torques can explain. Either simulations are missing crucial physics, or the alignments are telling us something about large-scale structure formation that lambda CDM does not capture. The cosmic microwave background shows its own alignment anomalies. The quadruple and octuple, mathematical descriptions of temperature patterns on large angular scales, are not oriented randomly as they should be. They align with each other and point toward directions that correlate suspiciously with the ecliptic plane of our solar system. This is called the axis of evil because it seems so improbable. The cosmic microwave background originates from the edge of the observable universe. It has nothing to do with our local solar system geometry. Finding correlations between the two makes no sense unless we occupy an extraordinarily special location, or the correlations are systematic errors we have not identified. Extensive studies have searched for instrumental effects or analysis choices that could create the axis of evil. None have been found that fully explain it. The pattern appears in data from multiple satellites processed by independent teams using different methods. It survives different approaches to removing foreground contamination from our galaxy. It remains when different parts of the sky are analysed separately. The axis of evil appears to be real, but if real, it challenges the assumption that the universe is isotropic. The hemispherical asymmetry in the cosmic microwave background adds to concerns. One half of the sky has slightly stronger temperature fluctuations than the other half. The difference is small, only a few percent, but statistically significant. Inflation predicts the universe should be perfectly isotropic. Temperature fluctuations should be the same in all directions. Finding hemispheric asymmetry suggests either inflation was not uniform, creating gradients across space, or something after inflation affected different regions differently. If the early universe had variations in how inflation proceeded, different regions would have different properties. The boundary between regions with different inflation histories might manifest as asymmetries in the cosmic microwave background. This is theoretically possible in some inflation models involving multiple fields or complicated potential energy landscapes, but it requires moving beyond the simple single-field inflation that works so well explaining other cosmic microwave background features. We would be complicating the model specifically to explain the asymmetry. Another explanation invokes bubble collisions. If our universe is one bubble among many in an eternally inflating multiverse, collisions with other bubbles during our early history could create asymmetries. Each collision would preferentially affect one direction, creating dipoles or hemispherical patterns. The cold spot discussed earlier might be one such collision signature. The hemispherical asymmetry might be another. The axis of evil might point toward where collisions occurred. This would explain multiple anomalies simultaneously, but requires the multiverse to be real and collisions to have occurred in ways we can observe. Large-scale flows of matter provide yet another anisotropy. The dark flow, if real, shows galaxy clusters across enormous regions, all moving in the same direction, as if pulled by mass beyond our cosmic horizon or pushed by forces we do not understand. This is directly incompatible with isotropy. After inflation, after the universe expanded from a tiny smooth patch to cosmic scales, matter motions should be random on large scales. Coherent flows spanning hundreds of millions of light years violate this expectation. They suggest either something beyond our horizon is affecting matter within it, or the cosmological principle is wrong, and the universe is not isotropic on the largest scales. Each alignment anomaly can potentially be explained. Galaxy spins might be measurement artifacts, or reflect physics we have not properly included in simulations. The axis of evil might be coincidence, an unlikely alignment we happen to observe. The hemispherical asymmetry might be early universe physics we do not fully understand. The dark flow might be systematic error in measuring galaxy velocities, but taken together, the anomalies create a pattern. Multiple independent observations all suggest the universe is not quite as isotropic as lambda CDM requires. The cosmological principle might be approximately true, but not exact. And if that principle is even slightly wrong, it calls into question whether lambda CDM can be correct, because the model fundamentally assumes perfect isotropy and homogeneity. The implications are profound. The cosmological principle is not just convenient, it is necessary for lambda CDM to work. If the universe is not isotropic, the entire framework of using a single cosmic time, coordinate, and assuming uniform expansion breaks down. Different regions might expand at different rates. Different directions might have different properties. The simple, elegant mathematics of lambda CDM would be replaced by something far more complex. We would need to track variations across space, account for large-scale flows and asymmetries, modify how we interpret observations. The model would become immensely more complicated with many more free parameters. We resist this not because we love simplicity for its own sake, but because lambda CDM works so well. Adding complexity without strong observational justification seems like desperation. But the observations are accumulating. The alignments are there in multiple datasets. The asymmetries persist despite searches for systematic errors. At some point, we must confront the possibility that the cosmological principle, foundational as it is, might be an approximation rather than exact truth. Perhaps the universe is only approximately isotropic on the scales we can observe. Perhaps we do not have access to large enough scales to average over all the variations and reach true homogeneity. Perhaps what we call the observable universe is just one region of a larger cosmos that has structure and variation on scales we cannot yet perceive. The alignment anomalies might be windows into this larger structure, hints that our piece of the universe, vast as it seems, is not representative of the whole. Evidence that lambda CDM, built on the assumption of perfect isotropy, is incomplete when tested carefully against the universe we actually observe, rather than the idealized universe we assume in our equations. Galaxies should form slowly. In the lambda CDM picture, structure grows hierarchically. Small dark matter halos form first when the universe is young. These halos merge over time to create larger halos. Gas falls into the halos, cools, condenses, and forms stars. Small galaxies build up gradually. They collide and merge into larger galaxies. The process takes time, billions of years. Early galaxies should be small, dim, irregular. Only after many mergers should large, mature galaxies with well-defined structures like spiral arms or elliptical shapes emerge. This is what simulations predict. Observations tell a different story. The James Webb Space Telescope, launched in late 2021 and beginning science operations in 2022, has revolutionized our view of the early universe. Its infrared vision pierces through cosmic dust and sees galaxies at redshifts previously difficult or impossible to observe. Light from these galaxies has been traveling toward us for over 13 billion years. We see them as they appeared just a few 100 million years after the Big Bang. Theory predicted these early galaxies should be small and faint. Webb found massive bright galaxies, some already containing billions of stars, with structures that look surprisingly mature. Within months of Webb's first observations, papers began appearing, describing galaxies at redshift 6, 8, even 12 or higher. Redshift measures how much the universe expanded since the light was emitted. Higher redshift means looking further back in time. Redshift 12 corresponds to seeing the universe when it was only about 300 million years old, roughly 2% of its current age. At that early epoch, Lambda CDM predicts only small proto-galaxies should exist. Yet Webb found candidates for mature galaxies with stellar masses exceeding 10 billion solar masses. These are not proto-galaxies slowly assembling. They are massive systems that have somehow already formed and settled into stable configurations. The galaxy candidates need spectroscopic confirmation. Images alone can be misleading. Some objects might be at lower redshifts than photometric estimates suggest. Contamination from foreground objects or unusual spectral properties could make galaxies appear more distant than they are. But even accounting for such possibilities, many high redshift galaxies have been spectroscopically confirmed. They are genuinely at the extreme distances and early times indicated. They are genuinely massive and bright when they should not be. How did these galaxies form so quickly? Star formation requires gas to cool and condense. Cooling takes time. Stars live for millions to billions of years, depending on mass. Assembling billions of stars requires many generations of star formation, or extremely high star formation rates, sustained over long periods. The earliest galaxies would have only a few 100 million years to build up their stellar content. That is a very short time cosmologically. Lambda CDM predicts star formation should be just beginning at these epochs, not already producing mature massive galaxies. Perhaps star formation was more efficient in the early universe than we think. Maybe the first stars formed faster, were more massive, and produced more heavy elements that facilitated subsequent star formation. Maybe gas cooling was more rapid in the dense environments of the early universe. These modifications might allow faster galaxy growth, but they require pushing star formation physics to extreme limits. Simulations implementing standard star formation prescriptions cannot produce the observed massive galaxies at such early times. Something about our models must be wrong. The problem extends beyond just mass. Some early galaxies show structures that should take billions of years to develop. Spiral arms form through gravitational instabilities and interactions that require many orbital periods to emerge. Elliptical galaxies form through major mergers between large spirals, processes that are violent and take time to settle. Finding well-formed structures at redshift 10 suggests these processes somehow operated much faster in the early universe than they do today, or that galaxies formed through entirely different mechanisms than the hierarchical assembly Lambda CDM describes. Dark matter physics might be involved. If dark matter is not cold, but has properties that allow earlier structure formation, this could help. Warm dark matter suppresses small-scale structure, but does not obviously accelerate large-scale structure formation. Self-interacting dark matter might affect halo properties in ways that facilitate earlier gas collapse and star formation. But these modifications would need to be finely tuned to solve the early galaxy problem without creating conflicts with other observations at lower redshifts where Lambda CDM works well. Modified gravity theories offer another approach. If gravity is stronger in the early universe, or on small scales, structure could grow faster. This would allow earlier formation of dark matter halos and the galaxies within them. Some modified gravity models make such predictions, but they must carefully avoid conflicting with other early universe observables like the cosmic microwave background, which matches Lambda CDM predictions beautifully. Modifying gravity after cosmic microwave background formation, but before significant galaxy formation, is a narrow window. Perhaps the issue is more fundamental. Perhaps the hierarchical assembly picture is too simplistic. Maybe galaxies do not only form through slow bottom-up merging of smaller systems. Perhaps some galaxies can form more directly from large collapsing gas clouds in the early universe. This top-down formation would bypass the gradual assembly process and could produce massive galaxies much earlier. But lambda CDM and simulations based on it do not predict such processes should be common. If they are important, our understanding of galaxy formation requires major revision. The early galaxy problem is still developing. Webb has only been operating for a short time. More observations will clarify which high redshift galaxy candidates are real and which are misidentified objects at lower redshifts. Better spectroscopic characterization will determine masses, ages, and structures more accurately. Perhaps the problem will diminish as observations refine. Perhaps the most extreme early galaxies will turn out to be less massive or less mature than initial estimates suggested. But current indications are that the problem is real. Numerous independent observations point to galaxies being more massive and more mature at high redshifts than lambda CDM predicts. This is not one or two outliers that might be flukes. This is a population of galaxies that are systematically different from predictions. The discrepancy suggests something about our model of the early universe is incomplete. This problem connects to others. If galaxies formed earlier and faster than expected, this might affect ionization, the process where the first stars and galaxies ionized hydrogen throughout the universe. Ionization timing constrains lambda CDM parameters. If it occurred differently than we think because galaxies formed differently, other cosmological parameters might be affected. The early galaxy problem might ripple through our understanding of cosmic history in ways we have not yet fully appreciated. It also raises questions about whether the universe had more time for structure formation than we think. If the Hubble constant is actually higher as local measurements suggest, the universe would be younger than the cosmic microwave background indicates. A younger universe makes the early galaxy problem worse because there is even less time for structures to form. But if the cosmic microwave background interpretation is wrong in some way, if the universe is actually older than we think, more time would be available. This seems backwards since the early galaxy problem suggests needing more time, not less. But perhaps there are connections we have not yet understood between expansion history, structure formation timing, and the properties of early galaxies. What is clear is that the early universe was more active and produced more mature structures sooner than lambda CDM predicted. The galaxies that should not yet exist are there in Webb's images, bright and massive, challenging our understanding of how cosmic structure emerges. Another crack in the model, another place where predictions meet observations and do not match. Another hint that lambda CDM, comprehensive as it is, cannot explain quite everything we see when we look carefully at the universe across its full history. Why now? This question haunts cosmologists studying dark energy. The universe is 13.88 billion years old. For the first 9 billion years, its expansion was decelerating. As gravity slowed, the expansion started by the Big Bang. Then about 5 billion years ago, something changed. Dark energy, which had always been present but negligible, came to dominate the universe's energy budget. Expansion began accelerating. This transition from deceleration to acceleration happened relatively recently in cosmic history. Not at the beginning, not in the far future, but during the past third of the universe's existence, during the epoch when intelligent life emerged on at least one planet and began studying cosmology. This seems like an extraordinary coincidence. Dark energy and matter have completely different properties. Matter density decreases as the universe expands. More volume means the same amount of matter is spread thinner, but dark energy density remains constant. The same amount of dark energy exists in every cubic meter of space, regardless of expansion. These two components evolve completely differently, yet their densities are comparable right now, within a factor of 2 of each other. For most of cosmic history, matter dominated overwhelmingly. In the far future, dark energy will dominate overwhelmingly. We happen to live during the brief transition period when both are important. The probability seems vanishingly small. Matter density has decreased by factors of billions since the Big Bang. Dark energy density has remained constant. These independently evolving quantities happen to be similar in magnitude during the precise cosmic epoch when observers exist to notice. Why should this be? Is it coincidence? Are we just extraordinarily lucky to exist when we do? Or does the coincidence tell us something deep about the universe or our place in it? This is called the cosmic coincidence problem. It is sometimes framed as asking why dark energy density is so small compared to natural particle physics scales, yet so large compared to matter density today. The vacuum energy that might constitute dark energy should be enormous, according to quantum field theory. We discussed earlier how the predicted value exceeds observations by 10 to the power of 120. That is the cosmological constant problem, why dark energy is not much larger. But even accepting the tiny observed value, why is it comparable to matter density now, rather than always negligible or always dominant? One response is anthropic reasoning. Perhaps the coincidence is selection bias. Observers can only exist during epochs when matter density is neither too high nor too low. If matter density is too high, the universe is too young and hot for complex structures. If too low, galaxies and stars never form. Intelligent life requires a Goldilocks epoch between these extremes. That epoch might naturally coincide with the transition from matter domination to dark energy domination. We observe this transition not because it is objectively special, but because we could not exist at significantly different epochs. This reasoning is controversial. Critics argue it abandons the goal of calculating dark energy from first principles in favor of saying we observe what we observe because we must. It does not explain why dark energy has its specific value, just why observers would find themselves at an epoch where dark energy and matter are comparable. The anthropic principle might be true, but it feels unsatisfying. We want to understand why rather than accepting that we observe what is required for our existence. Another approach is to make dark energy dynamical rather than constant. If dark energy density evolves with time in specific ways, perhaps the coincidence can be explained. Maybe dark energy was negligible in the early universe and only recently became important because some field driving it evolved to the right value. This would mean we do not observe coincidental similarity between dark energy and matter. Rather, dark energy became comparable to matter at a specific cosmic epoch determined by physics, and we happen to exist during that epoch. Many dynamical dark energy models have been proposed. Quintessence involves a scalar field slowly rolling down a potential energy curve, with the field's energy acting as dark energy. Phantom energy has equation of state more extreme than a cosmological constant. K-essence involves fields with non-standard kinetic terms. Each model makes different predictions for how dark energy density evolves with time and how the universe's expansion history differs from the standard cosmological constant case. The challenge is that observations constrain dynamical dark energy models severely. Dark energy appears constant within current measurement precision. If it evolves, it does so slowly enough that we cannot yet detect changes. This is another coincidence problem. If dark energy evolves, why is the evolution so slow that it appears nearly constant during the epochs we can observe? Why is it not evolving much faster or much slower? The problem shifts from explaining why dark energy density is what it is to explaining why its evolution rate is what it is. We have not gained much. Modified gravity provides yet another angle. Perhaps there is no dark energy at all. Perhaps gravity works differently on cosmological scales than general relativity predicts. These modifications could produce accelerated expansion without requiring any dark energy component. Some modified gravity theories can be tuned to have the transition from deceleration to acceleration occur at a specific epoch, but explaining why that epoch is now rather than earlier or later reintroduces the coincidence problem in a different form. Perhaps the coincidence is telling us our universe is part of a multiverse. If countless universes exist with different dark energy densities, observers would only emerge in universes where conditions permit structure formation and the development of life. Most universes would be either too dense and collapse quickly or have too much dark energy and expand so fast that structure never forms. We necessarily find ourselves in a rare universe with the right balance. The cosmic coincidence is selection bias across the multiverse. This explanation works but requires accepting the multiverse exists based on no direct evidence beyond solving the coincidence problem. Or perhaps the problem is not real. Maybe we are overestimating how coincidental the situation is. The transition epoch from matter domination to dark energy domination is not infinitesimally brief. It spans several billion years. Intelligent life could have emerged any time during this window. The fact that we emerged 5 billion years after the transition began, rather than immediately or in the far future, is not extraordinarily improbable. Given that life requires several billion years to evolve after planets form, and planets require previous generations of stars to create heavy elements, perhaps emerging during the dark energy domination epoch is actually fairly probable. The coincidence becomes less mysterious when you account for how long it takes for observers to emerge in any universe. Still, discomfort remains. Dark energy and matter are completely independent components. They evolve differently. They have nothing to do with each other physically, yet their densities are comparable within a factor of 2 during the present epoch. This is like two clocks with different mechanisms, one speeding up over time and one slowing down, both happening to show nearly the same time right now. Possible, yes, but suggestive that maybe they are not as independent as they appear. Perhaps dark energy and matter are connected in ways we do not understand. Perhaps one affects the other. Perhaps they are both manifestations of something deeper that we have not yet identified. The cosmic coincidence problem does not directly contradict lambda CDM. The model can accommodate any dark energy density and any epoch for matter-dark energy equality. But the problem is uncomfortable. It suggests our universe is special, or we are observing it at a special time. Physics hates special. We want to explain why things are the way they are through general principles, not accept special configurations as brute facts. The coincidence problem challenges us to explain why now. Why this balance between matter and dark energy during the epoch when beings exist to study cosmology. We have no good answer, just speculation about anthropic selection, dynamical dark energy, or connections between components we have not yet discovered. Another place where lambda CDM is silent when we want it to speak. Another question it cannot answer, despite its many successes. The cosmic microwave background is often described as the most perfect cosmological observation. Its temperature is uniform across the sky to 1 part in 100,000. Its tiny fluctuations match lambda CDM predictions with extraordinary precision. The power spectrum, describing how fluctuation strength varies with angular scale, fits theoretical calculations remarkably well. Hundreds of papers have analysed this data. Cosmological parameters have been constrained to percent-level precision. The cosmic microwave background is lambda CDM's greatest triumph. Yet even here, in this most successful observation, anomalies lurk, features that do not quite fit, patterns that should not exist, subtle but persistent deviations from the perfect match we would like to see. Start with the low multipoles. These describe temperature patterns on the largest angular scales, structures spanning more than 60 degrees across the sky. Lambda CDM predicts a specific amount of fluctuation power on these scales based on initial conditions from inflation. The observed power is lower than predicted, not dramatically lower. The measured values fall within about 2 sigma of predictions, but consistently lower across several multipoles. The probability is around 2 to 5%, depending on exactly which multipoles you examine and how you account for correlations between them. Not compelling evidence of a problem by itself, but suggestive. Why might large-scale power be suppressed? One possibility is that the universe is finite, smaller than we assume. If space has a finite size comparable to the observable universe, certain wavelength fluctuations cannot fit. Only specific modes are allowed, like standing waves on a string. This would suppress power on the very largest scales. The cosmic microwave background would show less correlation at large angles because fluctuations larger than the universe itself cannot exist. Some cosmologists have explored finite universe models that match the observed large-scale power better than infinite lambda CDM universes. But finite universe models create other issues. They must be carefully constructed to maintain isotropy. A universe with edges or boundaries would violate the cosmological principle unless the topology is special, like a three-dimensional analogue of the surface of a sphere or a torus. Such topologies are possible in general relativity, but require specific conditions we have no reason to believe are realized. We would be adding complexity to explain one observation without independent motivation. Another possibility is that inflation ended slightly earlier than standard models assume. If inflation lasted fewer e-foldings, quantum fluctuations on the very largest scales would not have been amplified as much. They would enter the observable universe with different properties, potentially suppressing large-scale power. This requires fine-tuning the duration of inflation, but is theoretically possible. Without understanding what ended inflation, we cannot rule this out. The axis of evil is more troubling. The quadrupole and octupole align with each other and point in directions that correlate with local solar system geometry. This should be impossible. The cosmic microwave background originates from the edge of the observable universe. It was emitted when the universe was 380,000 years old, long before our solar system formed. Local geometry from a tiny corner of space, billions of years later, should have no correlation with patterns in ancient light from cosmic distances. Yet the correlation exists. It has survived multiple satellite missions, multiple analysis teams, multiple attempts to explain it as systematic error or foreground contamination. The hemispherical asymmetry adds another layer. One hemisphere of the cosmic microwave background has slightly stronger fluctuations than the opposite hemisphere. The asymmetry is about 3%, small but statistically significant. Inflation should produce perfectly isotropic fluctuations. Finding asymmetry suggests either inflation was not uniform across space, or something after inflation affected different regions differently. Either interpretation requires modifying the simple, single-field slow-roll inflation that works so well explaining other features. Beyond these specific anomalies, detailed statistical tests find that the cosmic microwave background is not quite Gaussian. Gaussianity means fluctuations follow a bell curve distribution, which is what simple inflation models predict. Non-Gaussianity indicates more complex physics during inflation or processing of the fluctuations afterward. The detected non-Gaussianity is weak at the edge of significance. Different statistical tests give different results, some finding evidence and others not. But hints persist that fluctuations are slightly non-Gaussian in ways lambda CDM does not predict. Then there are the parity asymmetries. Fluctuations show slightly different properties depending on whether you analyze even or odd parity modes. This should not happen in isotropic inflation models. Parity should be conserved. Finding asymmetries suggests either systematic effects we have not identified or physics beyond standard inflation. Again, the signals are weak and controversial. Not every analysis finds them, but multiple studies report anomalies suggesting the cosmic microwave background is not perfectly symmetric under parity transformations. Each anomaly individually can be explained away. Cosmic variance, the unavoidable randomness from observing a single realization of the universe, means we might see unlikely features just by chance. With enough statistical tests, some will show apparent anomalies at 2 or 3 sigma significance, purely randomly. This is the look elsewhere effect. Search hard enough and you will find anomalies. But the cosmic microwave. Background anomalies are not random. They appear in specific places. The axis of evil points in a specific direction. The hemispherical asymmetry divides the sky along a specific axis. The low large-scale power affects specific multipoles. If these were purely random statistical fluctuations, they should not have such structure. Systematic errors provide another possible explanation. Foreground contamination from our galaxy, instrumental effects, analysis choices, all could potentially create spurious signals. Enormous effort has gone into understanding and removing foregrounds. The Planck satellite had 9 frequency channels specifically designed to separate foregrounds from the cosmic microwave. Background. Different component separation techniques give consistent results. It is unlikely that foregrounds explain all the anomalies, though they might contribute to some. What is clear is that the cosmic microwave background, precise as it is and successful as lambda CDM is at explaining it, shows features that are at tension with the model. Not overwhelming, not definitively ruling out lambda CDM, but persistently present and difficult to explain. These are the largest and oldest structures we can observe. Patterns imprinted when the universe was a tiny fraction of its current age. If something was different about the early universe, about inflation, about the physics governing cosmic evolution, the cosmic microwave background is where we would see it. And we do see things, small things, subtle things, things that might be nothing but that have persisted across decades of increasingly precise observations. Perhaps they are telling us that inflation was more complex than simple models describe. Perhaps the universe is not perfectly isotropic. Perhaps something from outside our cosmic horizon has influenced what we observe. Or perhaps lambda CDM is not quite the complete description of the early universe that we have assumed. The cosmic microwave background is lambda CDM's greatest success. But success is not perfection, and the imperfections, small as they are, might be clues to something deeper. Stand back, look at the full picture. Lambda CDM explains so much. The expansion of the universe, the cosmic microwave background, the abundances of elements, the formation of structure, galaxy clustering, gravitational lensing, supernova observations, countless phenomena across cosmic history, all explained by one elegant model with just 6 parameters. This is extraordinary, a triumph of theory and observation. We should celebrate it as one of humanity's greatest intellectual achievements. And we do, but we must also confront what it struggles to explain. The Hubble constant gives different values depending on the measurement method. A 5 sigma tension persisting over a decade despite enormous effort to resolve it. Matter clusters less strongly than predicted. Structure on very large scales exceeds what should exist. Small satellite galaxies are missing or behave oddly. Galaxies in the early universe are too massive and too mature. Dark energy and matter have comparable densities during precisely the epoch when observers emerge. The cosmic microwave background shows subtle asymmetries and alignments that should not exist. Galaxies align across distances where no physical process should coordinate them. Every one of these discrepancies can potentially be explained individually, but together they form a pattern. Lambda CDM is incomplete. What is missing? The honest answer is we do not know. If we knew, we would add it to the model and the problems would resolve. The fact that problems persist despite decades of work by thousands of researchers means the missing piece is not obvious. It is not something we can easily add. It requires either fundamentally rethinking aspects of the model or waiting for observations that definitively point toward the solution. We are in a period of uncertainty. The old model has cracks. The new model has not yet emerged. History suggests this uncomfortable phase precedes breakthroughs, but we cannot see the breakthrough from here. We can only enumerate possibilities and wait for observations to narrow them down. One possibility is that dark matter is more complex than lambda CDM assumes. Cold dark matter works well on large scales. It explains galaxy rotation curves, cluster dynamics, gravitational lensing. But on small scales, it struggles. Too many satellites predicted. Dark matter distributions in galactic centers do not quite match observations. Perhaps dark matter is not cold but warm, moving fast enough to prevent small-scale structure formation. Perhaps it is not just one particle species, but multiple particles with different properties. Perhaps dark matter self-interacts, scattering off itself in ways that redistribute it and affect structure formation. Each modification could potentially address some problems. None obviously fixes all of them without creating new tensions elsewhere. Another possibility is that dark energy is not constant. If it evolves with time, this could affect expansion history and structure growth rates. Perhaps dark energy was weaker in the past, allowing more time for structure formation and potentially explaining the early galaxy problem and large structures. Perhaps it is slightly different in different regions, creating the appearance of anisotropy. Perhaps it couples to matter or dark matter, affecting clustering in ways we have not accounted for. Dynamical dark energy requires adding parameters and complicating the model. It must be carefully tuned to avoid conflicting with the many observations lambda CDM explains successfully. But it remains a possibility worth exploring. Modified gravity is the most radical option. Perhaps general relativity, spectacularly successful as it is, requires corrections on cosmological scales. Perhaps gravity is stronger or weaker than predicted in certain regimes. Perhaps additional gravitational degrees of freedom exist beyond those in general relativity. Dozens of modified gravity theories have been proposed. Some are designed to eliminate dark energy, explaining acceleration through gravitational physics. Others aim to replace dark matter, modifying gravity to produce effects that mimic dark matter's influence. A few attempt both. Most fail some observational test. The detection of gravitational waves from neutron star mergers in 2017 constrained modified gravity severely. Gravitational waves must propagate at the speed of light. This rules out many modifications, but not all. Some modified gravity theories survive and could potentially address lambda CDM tensions. Perhaps the issue is not the physics, but the framework. Lambda CDM assumes the cosmological principle that the universe is isotropic and homogeneous on large scales. But what if this is only approximately true? What if our observable universe is a region within a larger, inhomogeneous cosmos? What if matter distribution varies significantly on scales larger than we can observe? Local variations in matter density affect expansion rates. If we are in an underdense region, a large void, our local expansion rate would differ from the cosmic average. This might explain the Hubble tension. Local variations could also affect how we interpret the cosmic microwave background and structure formation. we would not be observing a representative piece of the universe, but a special region. Lambda CDM would work well for the universe as a whole, but fail locally. Or perhaps the multiverse is real, and we are seeing its effects. If our universe is one bubble among many, interactions with neighboring bubbles during early cosmic history could create asymmetries, suppress large-scale power, even affect expansion history. Bubble collisions would leave signatures in the cosmic microwave background. Multiple collisions from different directions might create complex patterns of asymmetries and alignments. This would explain several anomalies simultaneously, but it requires accepting the multiverse based on indirect evidence. No observation definitively proves other universes exist. We would be invoking unobservable entities to explain observations, always a dangerous step. Perhaps the answer involves new physics beyond the standard model of particle physics. Lambda CDM incorporates known particles and forces, but we know the standard model is incomplete. It does not include gravity, it does not explain dark matter or neutrino masses or matter-antimatter asymmetry. Extensions like supersymmetry or extra dimensions might affect cosmology. New particles or fields active in the early universe could alter structure formation or expansion history. String theory predicts vast landscapes of possible vacuum states, each with different physics. Perhaps our universe occupies one particular state, and properties of that state affect cosmology in ways we have not incorporated. What seems clear is that Lambda CDM is not the final word. It is immensely successful. It will remain the foundation for cosmology even as we extend or modify it, but extension or modification is coming. The tensions are too numerous and too persistent to ignore. The observations are too precise to attribute discrepancies to measurement error. Something about our model is incomplete. Within the next decade, multiple new observational programs will provide data precise enough to distinguish between possibilities. The Vera Rubin Observatory, Euclid Roman CMBS4, next-generation gravitational wave detectors, all will constrain cosmological models with unprecedented precision. The tensions will either resolve as better data clarifies what is happening, or they will strengthen and force us to abandon or significantly modify Lambda CDM. We are at a pivotal moment in cosmology. The standard model has reigned for decades. It has been tested and confirmed repeatedly. But cracks are appearing, small cracks, not yet bringing down the edifice, but widening with each new precise observation. History suggests such moments precede revolutions. Classical mechanics showed cracks before relativity, and quantum mechanics emerged. The standard model of particle physics showed tensions before the discovery of the Higgs boson and neutrino masses. Perhaps cosmology is approaching its next revolution. Perhaps the problems with Lambda CDM are symptoms of missing physics that, once discovered, will seem obvious in retrospect. We cannot see it yet. But the universe is trying to tell us, through these persistent anomalies, we just have not learned to listen properly. Not yet. But we are working on it. And the answer, whatever it is, will reshape our understanding of the cosmos as profoundly as anything that has come before. The problems with Lambda CDM are not the end of cosmology. They are the beginning of something new. For a century, we have built cosmology from nearly nothing. A few observations of galaxy velocities, vague ideas about cosmic evolution, no understanding of what most of the universe contained or how it worked. We have progressed from ignorance to having a detailed model explaining countless phenomena. That model is incomplete, but incompleteness is not failure, it is opportunity. The places where models fail are exactly where we learn, where new physics reveals itself, where understanding deepens. Lambda CDM's problems are gifts. They tell us where to look next, what questions to ask, what observations will illuminate the path forward. The next decade will be transformative. Multiple observational programs coming online will test lambda CDM with unprecedented precision. The Vera Rubin Observatory in Chile will begin operations soon, photographing the entire southern sky repeatedly over 10 years. This legacy survey of space and time will detect billions of galaxies, measure their positions, shapes, colors, redshifts. The data will map the universe's large-scale structure in exquisite detail. Any anisotropies or anomalies in how matter is distributed will become unmistakable. The clustering tension will either be confirmed at overwhelming significance or shown to be systematic errors. Large structures that should not exist will either proliferate as we observe larger volumes or disappear as better measurements reveal they are not as extreme as early estimates suggested. The Euclid Space Telescope, launched by the European Space Agency, is already observing. Its mission is to map the geometry and structure of the dark universe. Weak gravitational lensing measurements will trace how dark matter is distributed. Galaxy clustering measurements will constrain how dark energy has affected expansion over cosmic time. Euclid will determine whether dark energy is truly constant or evolves, whether the clustering tension is real, whether lambda CDM's predictions for structure formation match reality across redshift. The data will be precise enough to distinguish between competing models that currently fit observations within uncertainties. NASA's Nancy Grace Roman Space Telescope will launch in the mid-2020s. Roman's infrared capabilities will complement Euclid and Webb. It will measure distances to hundreds of millions of galaxies using multiple techniques. The expansion history will be traced with precision that should definitively resolve the Hubble tension. Either local measurements or cosmic microwave background interpretations will be shown wrong, or we will confirm that the tension is real and demands new physics. Roman will also study the early universe, characterizing galaxies at high redshift to determine whether the early galaxy problem is genuine or an artifact of small number statistics from Webb's relatively small survey areas. The James Webb Space Telescope continues revolutionizing high redshift astronomy. Its first years have produced remarkable discoveries, but the full potential will take years to realize. Large surveys with Webb will characterize hundreds of early galaxies, providing statistical samples rather than just interesting individual objects. Spectroscopy will determine their masses, ages, and compositions precisely. We will learn whether early galaxies really are as massive and mature as initial observations suggest, or whether we are seeing unusual examples. We will understand how star formation proceeded in the early universe, and whether lambda CDM's predictions match reality. CMB-S4, the next generation cosmic microwave background experiment, will map the ancient lights with sensitivity limited only by fundamental astrophysical foregrounds. Deploying in the late 2020s at sites in Antarctica and Chile, CMB-S4 will measure temperature and polarization fluctuations at levels where every cosmic microwave background photon is counted. The large-scale anomalies will either be confirmed as real features demanding explanation or shown to be statistical flukes that disappear with better data. New tests of inflation will probe the earliest moments of cosmic history. Measurements of gravitational lensing of the cosmic microwave background will constrain dark matter and neutrino properties. Everything lambda CDM predicts about the early universe will be tested at the highest precision achievable. Gravitational wave astronomy is entering its prime. LIGO, Virgo, and CAGRA are detecting black hole and neutron star mergers regularly. LIGO India will join soon, improving localization and detection capabilities. These observations provide independent measurements of cosmic expansion through the gravitational wave luminosity distance. As more mergers are detected, especially those with electromagnetic counterparts, allowing precise redshift measurement, The expansion history will be traced using completely different physics than electromagnetic observations. This might resolve the Hubble tension by showing which measurement method is more reliable. Next-generation ground-based detectors like the Einstein telescope in Europe and Cosmic Explorer in the United States will improve sensitivity by factors of 10. They will detect thousands of mergers per year, observing back to redshifts where the first black holes formed. The merger history will test whether black holes and galaxies evolved as lambda CDM predicts. Gravitational waves from the early universe might be detected, revealing physics from epochs no electromagnetic observation can access. And perhaps, just perhaps, echoes or other signatures will reveal whether the objects we call black holes are actually something stranger. The Square Kilometre Array, currently under construction in Australia and South Africa, will be the world's most powerful radio telescope. Its square kilometre of collecting area will detect radio waves from hydrogen gas throughout the universe. This neutral hydrogen traces matter distributions invisible to optical telescopes. The SKA will map the cosmic web at redshifts where lambda CDM makes specific predictions about structure. It will measure galaxy motions across enormous volumes, testing whether large-scale flows like the dark flow exist or are measurement artifacts. It will study the early universe during the epoch of ionization, when the first stars and galaxies formed. Every test will either confirm lambda CDM or reveal discrepancies demanding explanation. Beyond specific experiments, computational cosmology continues advancing. Simulations with trillions of particles now capture the universe's evolution across cosmic history with stunning realism. As computing power increases and physics implementations improve, simulations will make increasingly precise predictions that can be compared to observations. If lambda CDM is correct, simulations will converge with observations across all scales and epochs. If lambda CDM is incomplete, discrepancies between simulations and observations will clarify exactly where new physics is needed. Simulation is not just theoretical exercise, but crucial tool for understanding whether our models capture reality. Theory is also advancing. Researchers explore extensions and modifications of lambda CDM, seeking models that explain the tensions while maintaining the successes. This is not easy. Adding parameters to fix one problem often creates conflicts elsewhere. The search for theoretical frameworks that improve on lambda CDM across the board is ongoing and challenging. But progress happens. New ideas about dark matter, dark energy, modified gravity, inflation, all are being developed and tested. When observations finally point clearly toward what is missing from lambda CDM, theory will be ready with candidate explanations that can be immediately evaluated. What is certain is that cosmology will not remain static. We are not approaching the end of cosmological discovery, but entering a new phase. Lambda CDM has taken us far, but the universe is more complex than any model we have constructed. The problems we face are not signs of failure, but indicators that we are pushing into territory where our understanding is incomplete. This is exciting. This is why we do science, not to confirm what we already believe, but to discover what we do not yet know. The tensions in lambda CDM are opportunities. They point toward discoveries that will deepen and extend our understanding of the cosmos. Within our lifetimes, perhaps within the next decade, we will likely see cosmology transformed. New physics will emerge. Lambda CDM will be recognized as an approximation, a limiting case of something deeper, and we will understand the universe better because we confronted the problems honestly rather than dismissing them. There is a problem with our model of the universe, but problems are how science progresses. They are how we learn, and what we are about to learn will be extraordinary.